All right, so we're going to take a look at 3.5, which is on basically what we've been doing all week, but now we're not going to ignore complex answers, whether they're complex answers from quadratic formula, that can happen, or complex answers when we have to use synthetic division. We're going to do that. So just a reminder what it means if a number is a 0. It means that if you plug it into an equation, you will get 0 as the answer. It also means that that number, comma 0, is an x-intercept. Now, if you think about complex roots, they don't show up on a graph. So the graphing calculator, in terms of graphing an equation, is useless to be able to find complex roots that are imaginary. If they're real, sure, you'll see them cross the x-axis. But if they're imaginary and they're a root, they are not an x-intercept. Okay? This x-intercept thing only applies to real numbers, not imaginary. So if a polynomial doesn't cross the x-axis at all, then it has no real zeros. So if a polynomial doesn't cross the x-axis, there are no real zeros. It doesn't mean there are no zeros. It just means they're not real. When we solve equations, there are always as many answers as the highest exponent. Always. Sometimes those answers are real, sometimes they're complex, sometimes it's a mixture of the two. But let's look at this one. Now, we know that if we graph this, this is a parabola shifted up one. It basically would look like that. It doesn't have any x-intercepts. So if we try to solve this, and we subtract 1 from each, let's say we set it equal to 0, because we're going to try to find the roots. So set it equal to 0, subtract 1 from each side, and how would we get rid of that exponent of 2? We would take the square root of each side, and we get x equals the square root of -1. Well, we know from when we dealt with real numbers, we can't take the square root of a negative. When we're going to deal with imaginaries and complex numbers, you can. All right, so that's what we'll briefly talk about, this kind of overview of complex numbers, and then we'll get into problems that might have something like a complex number as the answer. So we'll try something like that after. The techniques that we're going to use to find roots are the same. We can use the rational root theorem, we can use synthetic division, we can use the quadratic formula. It's just now all those things might result in imaginaries. So let's quickly go over a couple things with imaginaries. Okay, so first thing is when we deal with imaginary numbers, I is the symbol they use to represent the square root of -1. This is not something you can prove. It's just because it is. Okay? It's kind of like proving why parallel lines don't cross. You can't. That's a basic thing that you just go with. Parallel lines don't cross. I equals the square root of -1. Can't prove it. Just that's what it is. So in this sense, I is a number. It is not a letter. I mean, it is a letter in the English alphabet, but in math, we're using it as the symbol for a number. Just like this. You would never use this as a variable in math.
Oh, yeah.
I mean, it's a letter. Yes, it is a letter from the Greek alphabet. Usually you use letters as variables, but this is a special letter. It's a special letter that means 3.14. This is a special letter that means square root of -1. It's the same idea.
So that's I squared, just -1.
So I squared would be -1. Yep. So if we plug I into the problem that we just had, watch what happens. You get y equals I squared plus 1. But what did we just say I squared was?
Negative 1.
-1. So if we plug I in and we get 0 as the answer, what does that mean I is in this equation? Well, we plugged I in for x. It's a root. I is the root of the equation. I is the 0. Don't say I is the x-intercept. That's not true. But it is the root and it is the 0. And we're going to talk more about this, but if I is a root, x minus I is a factor. Just like if 3 was a root, x minus 3 is a factor. So x minus I is a factor. We'll talk more about that. So complex numbers have, the way we generally write them is we have two parts. The first part is real, and the second part is imaginary. If I ask you, for example, what the real part of that number is that I just circled, it's 2. The imaginary part, just 3. The I is there to tell you what's next to it is imaginary. Now, the first one, this is called a pure imaginary number because it doesn't have a real part added to it. This is also a pure imaginary number. That's a real number. Technically, it is still considered complex because if you think of complex numbers, you can break them up into two groups, reals and imaginaries. So complex is the big category. That includes every kind of number you've ever studied. And two kind of subcategories under that are real and imaginary. Real and imaginary. This last one, 2/5 minus I, that's a complex number that has both a real and an imaginary part. Any questions on the format of how you write a complex number?
Wait, how is 4? Just
4 would be considered a complex number, and the imaginary part is 0.
so isn't any number?
Questions on that? Okay, so when we talk about two complex numbers being equal to each other, what that would mean is the real parts match each other and the imaginary parts match each other. If only part of that is true, then the complex numbers are not equal. Like you can't say 3 plus 2i is the same as 3 plus 8i. Well, yeah, but the real parts are equal, but the imaginary parts are not. So in order for two complex numbers to be equal, both parts, real and real, and imaginary, would have to match each other.
So they always just have to be the same exact thing?
Yeah. So like if you wanted to like build a computer program to check if two complex numbers were equal, you'd have to check two things. You'd have to say, okay, check the first number and see if it matches the first number. Check the second number and see if it matches the second number. You can't just check one of them. You have to check both.
Can you tell me if they're the same by looking at them because they're the same? How do you need to know that?
Yes, my brain knows that.
Okay.
But if you actually want to like really boil it down and say, what does it mean for two complex numbers to be equal to each other? It means the real part matches the real part, and the imaginary part matches the imaginary part. That's just more specific than saying they look the same.
Yeah.
What does look the same mean? It means what I just said. Yeah. So we're going to look at adding, subtracting, multiplying, and dividing complex numbers really quick. Okay, something you did back in Algebra 2. And I know I told you that I is a number, like the Greek letter pi. We use that as a number now. But if you treat I as a letter, when you combine like terms, it follows all the same rules. So like 2i plus 3i, it is 5i. Just like 2x plus 3x is 5x. It follows that same idea. So we'll try to think of it as a letter when we combine like terms. Whenever we multiply, we're going to end up using the double distributive property, or foiling. We're going to end up with some I squareds. If you ever get an I squared, you need to change it to -1. Do not leave I squared in the answer. When we do division, I'm going to show you how to do it with what's called a conjugate. And conjugates are something we're going to use several times, especially when we get into trade. We're going to talk about conjugates again. But we're going to use the conjugate trick here to do division. And let's look at what happens with square roots. When I write the square root of -x, what number is really in front of the x?
Or square root of -x or
Square root of -x. There's really a -1 in front of it, so you could think of it that way. It's the square root of -1 times x. And whenever you have a product under a square root, you can break the square root apart like that and do the square root of each one separate. This we just talked about. What's the square root of -1? I. So the answer there is I square root of x. Couple things about the notation. What? Couple things about the notation. When you have a square root that you can't simplify, like square root of 7, you would write it with the I in the front. We don't want to put the I after a square root, because if you do that, why would it not be a good idea to do that? Yeah?
It looks like I is under it.
Yeah, it looks like I is under it. So if you put the I before it, then it eliminates any confusion where the I is. So always put the I before a square root. But if you have a square root that you could simplify, generally we would write something like that as 2i. It is okay to put the I after it in that case because the square root is gone. You usually don't write I2. It's just not how they write it. Okay, so I comes before it. When you have a square root, you can't simplify. But if you can, then put the letter where you would normally put it when it has a number next to it. The letter comes second.
Alright, and the I before square root of 4 means that it's equal to the square root of -4.
Yeah, the square root of -4 would be 2i. We're gonna go through some right now. Yeah.
What if it was a square root like the square root of something that doesn't completely get rid of the square root sign?
Like the square root of -7?
Like something you can
Like the square root of -20?
yeah. So like you can take
Yeah, we're gonna do it.
okay.
Yeah.
Yeah.
So the idea, if you look at the pattern here, what happens is if you have a negative under a square root, to write the final answer, the negative comes out of the square root as an I.
I see.
That's the pattern. The negative comes out as an I, and you're still left with the square root of whatever you had, and then you do the problem from there. So in this one, the negative is going to come out as an I, and I'm still left with the square root of 4, which is how much? 2. So the answer to this is 2i. That's the square root of -4. How about the square root of -9?
I square root of 3. Or I 3. 3i.
Yeah, this is very 3i. When you said I3, that one was technically okay. 3i would be the best way. How about square root of negative 7? That one, all we can do is I square root of 7. We don't ever want to leave a negative under the root, so we pull that out as an I because of what I showed you. But square root of 7, you're left with. Now, this one, you'd start by pulling the negative out. And now do the rest of that problem for square root of 20. What is the square root of 20? Forget about the I for a second.
It's 2 square root of 5.
So this is 2i square root of 5. That's where you put the I. You could do I2, but you won't see that.
Interesting.
Okay, so that's square roots. Okay, let's try adding. So to add complex numbers, all you have to do is combine like terms. Combine your reals, combine your imaginaries. When I add these together, what do I get for the real part of my answer? 11. We had a 7. We added a 4. We get 11. How about the imaginary part? Plus 2i. And that's adding complex numbers. That's it. Subtracting. Very similar, except think of the minus sign, it's being distributed. You are subtracting both parts of what's inside there. So if I do this one, what do I get for a real part? Negative 2. And my imaginary part? Negative 3i. Because it's negative 2 minus I. Negative 2 minus 1 is negative 3. Adding and subtracting is really straightforward. Any questions on that? Okay, multiplying. Well, multiplying is pretty straightforward. You have to use distributive property. You would not use the double distributive property on these because the plus sign is between it. If you saw something like that, that would mean to multiply. So no symbol between the parentheses, you're multiplying. Even if it didn't say multiplying, it just said simplify it. You know it's multiplication. All right, so let's distribute it out. So we're going to go like that, and then we're going to go like that. When you're done, your answer should look like this. You're going to have a real part, plus or minus, an imaginary part, and then an I. I don't know if it's a plus or it's a minus, depends on the problem. It'll be one or the other. But we need to fill in these two boxes. Okay, let's do it out. 2 times 5 gives me 10. What's that part? Negative 2i. And the inner? 15i, which is 13i. That was 5. 3i times negative I. So think about it first. It's a positive times a negative, which is y. So that's a negative. And then what's 3i times I? 3i squared. So 3i times I is 3i squared. And it was negative because it was a positive times a negative. Now, what is I squared? That's negative 1. So really it's 10 plus 13i minus 3 times negative 1, which is what? 3. So really it's 13 plus 13i. Just a coincidence they came out the same? That usually doesn't happen. But that's multiplying. A little bit more involved than adding and subtracting, but still not too bad. Any questions on multiplying? Okay. And the last one before we can do the actual thing in the lesson. So conjugates. Conjugates are what we're going to use when we do division. And a conjugate is when you take the imaginary part of a complex number and you make it the opposite of what it is now. It's called negate. Negate means to do the opposite. So let's just practice. If you had 3 plus 2i, what would be the conjugate of 3 plus 2i?
3 minus 2i. Is that or is it just both the sign? 3 minus 2i.
Well, it says to just negate the imaginary part. It doesn't say to do anything to the real part.
3 minus 2i.
So it's 3 minus 2i. How about 4 minus 5i? 4 plus 5i. How about 3i?
Minus 3.
Negative 3i. Yep. And how about 6?
Just 6.
Just 6. Because when you change the imaginary part of the number 6, think of it like this. You started with 6 plus 0i. The conjugate is 6 minus 0i. Well, that's the same thing. 6. So any questions on how to find conjugates? Once we know how to find a conjugate, then we can do that to do the last thing that's review, which is division.
Wait, so what was 6 say the same?
Because the conjugate would be 6 minus 0i, which is the same as 6 plus 0i. So now, to divide two complex numbers, what you end up doing is multiplying the top and the bottom by the conjugate of what's in the bottom. The reason we do that is because when you divide complex numbers, you cannot leave an I in the bottom. You have to get rid of it. And the easiest way to get rid of an I in the bottom is to multiply it by its conjugate, and it will cause the I to cancel out. But if you multiply by it in the bottom, you have to do it in the top. So your final answer to every problem should look something like this. Real part, imaginary part, and then an I, and either a plus or a minus. Not both, one or the other. Okay, let's try this one. So they want us to divide 5 plus I by 2 minus 3i. Well, that's the first thing I usually do. Put everything in parentheses.
Wait, alright, so I should say to multiply numerator conjugate
By the conjugate of the denominator. It has to be the conjugate of the bottom. So, what's the conjugate of the bottom in this case? Yeah?
2 plus 3.
2 plus 3i. Now, I can tell you very quickly, the bottom is 13. And the quick way I did that, if you FOIL this out, you get 2 times 2 is 4. But then you get 2 times 3i, which is what?
What? 6i.
6i. But then 2 times negative 3i. So you don't have to worry about the outer and the inner when you FOIL conjugates because they cancel each other out. So the only thing you really have to do is 2 times 2, which is 4. And then negative 3i times positive 3i. Well, negative times positive is negative. What's 3i times 3i? I squared. But I squared is negative 1, so effectively it makes that a plus. And that's how I quickly got 13 in my head. So all I did in my head was I did 2 squared plus 3 squared. If you don't want to use that shortcut, it's fine. Just FOIL it all out, and you'll get the same thing. Now the top, you do have to FOIL it out. Okay, so let's do that. So 5 times 2 gives me 10. 5 times 3i plus that, 17i. And let's see if we can do the last part all at once. What's I times 3i?
3i squared.
Okay, 3i squared. But that is,
It's just negative.
that's negative 3.
What was the original
Which
answer?
becomes 7 plus 17.
3i squared.
So 7 plus 17i over 13. But that's not set up like that. So how do we fix that fraction so that it has the real part in one box and the imaginary part in the other? What would my real part be here? Yep.
Multiply 13 by 7 and 17.
Well, how would you write this? If I said to write that as two separate fractions.
Oh, two separate fractions.
Yeah.
Oh,
Think about if you had it before you found a common denominator and put it all together, separate it back out.
2 9 plus 8 9.
Yeah.
Oh.
2 9ths plus 8 9ths. So what about here?
Oh, 7 13ths plus 17
Perfect. That's how you write your answer. 7 13ths plus 17 13ths. You could keep the I in the top. A lot of times they put the I right in the middle when they do that. All right, so that hopefully was mostly review. Okay, that's all.
What?
So that was all Algebra 2 stuff with complex numbers. So now we're going to look at the actual lesson, which was finding the zeros and the roots. So keep in mind everything we've learned. It all works with complex numbers. But this one, you're not going to have to use rational root theorem, because if you have an equation that's already quadratic, you already know how to solve it. You don't have to do synthetic division. The whole point of that is to take your exponent down a number. We don't need to. So, what's one way you can solve a quadratic? Yep. Right, and that's the way you're going to have to do it here. It will not factor. Okay, this will not factor. So, what's A in this case?
1.
B? See? 1. So they're all 1s. So let's do the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2. So that's going to give me negative 1 plus or minus, what's going to end up under the square root?
Negative 4. Or negative 3.
We're going to end up with the square root of negative 3. This is why we talked about square roots. How do you write the square root of negative 3?
I square root of 3.
I square root of 3 over 2. Now, we're at the same step we were in the last problem. You should split this into your real and your imaginary. So your real is negative 1/2 plus or minus, and the imaginary is root 3 over 2i. Now, I said you shouldn't put an I after a square root, but when it's a square root with a fraction, I don't think there's any confusion about where this I is. You shouldn't be confused if it's under the square root or not, because I put it way out in front in the middle. And that's it. That's how you'd find your two answers. So we know those would be roots. Those would be zeros. Would they be x-intercepts? No, because they're imaginary. You would not be able to get these on the calculator.
So is the calculator going to be any help?
Yes, it will. Yes. So if you look at those two answers, negative 1/2 plus root 3 over 2i, negative 1/2 minus root 3 over 2i. What do we call these two things? Well, they're complex numbers, but it's like 3 plus 2i, 3 minus 2i. Those are called, they're conjugates. When you solve for roots, complex roots always occur just like that. they always come in pairs. Always. So if I tell you that x plus I is a root, or a factor to a problem, if x plus I is a factor, then you know x minus I is a factor. Complex roots always come in pairs. You cannot get an odd amount of them. They come in pairs. So in the very first problem we looked at, let me just go back for a second. I said to you to plug I in, and it worked here. And since it worked, I told you x minus I was a factor. What else would be the other factor automatically? X plus I. And that is how that factors. It factors as x plus I, x minus I. If you FOIL this out, that's exactly what you get. You get x squared plus 1. So that's an example of factoring with complex numbers. So if you know that a minus bi is a root, then a plus bi is a root. They always occur in conjugate pairs. Now, everything we've learned, the remainder theorem, the factor theorem, and synthetic division, all work with complex numbers. And it's a little annoying to do synthetic division with a complex number, but we'll do one just to try it, and that'll be it for that part. Okay, so to show that 1 minus 2i is a root, we're going to divide through synthetically by it and hope that what happens? We get a remainder of 0. Now, when we do this, you're going to want to leave a little bit of room to do some scrap work off to the side, because there's some calculations we're going to have to do outside of the synthetic division, because the multiply step in synthetic division is not as easy. It ends up being a FOIL every time. So you've got 1 minus 2i on the outside. Fill in your coefficients. 4, 17, 0, 14, 65. Okay, first part's not there. Bring down the 4. 4 times 1 minus 2i, that's a distributive property, but for now it's just a single distributive. So what's 4 times 1 minus 2i?
4 minus 8.
Yep. Now add these up. 17 and 4 gives me 21. Yes.
The 17 is x squared, so you should swap the.
Oh, did I copy it wrong? 4.
Should be 0. That's it.
Oh, that should be a 0. Thank you. I put the 0 in the wrong spot. I don't think it messed us up yet, but it was just about to. Are we good now? 4, 0, 17. Yeah, we're good. All right, so we multiply by the 4. That's fine. Now add these up. So adding with 0 stays the same. And now, off to the side, we're going to multiply 1 minus 2i and 4 minus 8i. So we're going to end up doing 3 multiplication problems here that are FOIL. So we want to get pretty quick at FOILing if we can. Okay, what's 1 times 4? Minus 8i. 1 times negative 8 minus 8i minus another 8i. Negative 16i. And what's negative 2i times negative 8i?
16 squared.
That would be a positive 16i squared, which is really negative 16. So negative 12 minus 16i. Not too bad, just a little annoying. Add these up. Nothing to combine with the I, but what's 17 plus negative 12? 5. And let's do it again. So 1 minus 2i times 5 minus 16i. Okay, 1 times 5. 1 times negative 16i. 5i times negative 10i. I'm sorry, never mind. 5i times negative 2i. Negative 10i. And negative 16 minus 10. Negative 2i times negative 16i. Negative 32. Because that's 16i squared. Alright, 5 minus 32 gives me negative. Question? So yeah, negative 2 times negative 16 is positive 32. But then the I times I is I squared, which becomes a minus 32. So 5 minus 32 was how much? Negative 27. And was it 26i?
Yeah.
Okay. What's 14 plus negative 27? Negative 13. And now, this last step, we should get negative 65 right here. The I should disappear. All right, let's see. 1 minus 2i times negative 13 minus 26i. All right, 1 times negative 13.
Negative 13.
And then that's negative 26i. And then what's negative 2i times negative 13? Positive 26i. So those are gone. And negative times negative, that's a positive. 52. So it's a positive 52i squared, which is what? Negative 52. And what's negative 13 plus negative 52? There we go. So I generally would not want to have to do it that many times, maybe with a cubic, so we could chop off one round of that, because if you can do it that many times, you could do it one less time. But that's how synthetic division will work. Exactly the same, just the multiplication is a few more steps.
Jeez, that was a lot.
Yeah, it takes a little longer.
Yes, give us much more room.
Okay, so any question on how we just proved 1 minus 2i was a root? Okay.
Alright, do you need to write that in like the final form after?
No, because it wouldn't make sense. It would be really strange. That you're done. Once you get a 0, you're done. So think about an odd degree polynomial, like a cubic or a 5th power, 7th power. How come they always will have at least one real 0? Yeah?
They're always either up, down, or down, up.
Right, the end behavior is up, down, or down, up. Since they go up and down forever, they're going to have to cross the x-axis at least one time, maybe more. Depends if they do some turns. But they're definitely going to cross at least one time. That is not true about even roots. Think of a parabola. A parabola shifted up never crosses. So with even polynomials, it is possible to get no real answers. With odd, it's not. And that's the whole key to solving an odd. You always are going to have at least one real root. And if I'm nice, I'll always give you one real root that's rational so you can find it. Because if you can find a root that's rational, you can divide through by it and then turn your cubic into a quadratic and then solve it with quadratic formula or factor it. But you have to be able to find a rational root first. How are we going to find a rational root for x cubed minus 1? So how do you find a rational root for a polynomial? What do you use? Yep. Use the rational root theorem. So figure out your p and your q. What are my p's in this case? And my q's? So the only possible rational roots for this problem are 1 or -1. I can check them quicker than I can by graphing that. Which number, when you plug it into x cubed minus 1, gives you 0? Positive 1. So I know positive 1 is a root. If this was more complicated, I might not be able to figure that out. Okay, I'd graph it. And then I would look at the graph, like we did yesterday, and then go from the graph and see which one looks right. But I don't even need a graph for this one. So the roots here are positive 1. And there are 2 more. There have to be 3. They could be both imaginary, or they could both be real. Okay, it could be either one. Now that I know 1 is a root, what do I do with it to turn my cubic into a quadratic? Do synthetic division. So put your root on the outside. 1, 0, 0, -1. Okay, 1 times 1 gives me
1.
0 plus 1, 1. 1 times 1, 0 plus 1,
1.
5 plus 7.
What? No,
Just kidding.
not 1. It's not 1.
1 times 1,
1.
1, 0.
0. Yay.
So we know that 1 is a root. I already knew that 1 was a root. I'm more interested in this. What does that tell me?
X squared plus x plus 1.
X squared plus x plus 1. We already did that problem. So from here, that's how you find the rest of your answers. So it's -1/2 plus or minus root 3 over 2 I. So the other roots, -1/2 plus or minus root 3 over 2 I. And I'll just put a note here. See previous, or maybe it was the one before, previous example. But you never would have been able to get it to this point if you hadn't found a rational root first. You have to be able to do that. So there always will be. All right, so in example 6, this was the problem we solved. Right? We set it equal to 0, and we found the 3 answers. Now, somebody might try to solve this in Algebra 1. They don't know about the rational root theorem or any of that stuff. So they may just say, oh, add 1 to each side, and then just take the cube root. Okay, well, that'll give you this answer, the cube root of 1. I can take the cube root of each side. But the problem is that whole method does nothing to find the complex, the imaginary answers. So essentially what we did in this problem is we solved this equation. So what did we do? We solved for the cube roots of 1. All of the cube roots. The real ones and the imaginary ones. Those are the cube roots of the number 1. All 3 of them. 1 and then the imaginaries. And that's what this is saying. So you might not have thought of it that way, but that's what we did in example 6. We found the cube roots of the number 1. If you solved this equation, think about adding 1 to each side. Taking the 4th root of each side, you would be finding the 4th roots of 1. The problem with this approach is you don't get the imaginaries. So you have to do the synthetic division and rational root theorem to figure those out. Sometimes when they say finding like the cube roots of 1 or the square roots of 1, they call that the cube roots of unity. Not sure why they give a special name to 1, because if it's anything else, you just say the square roots of 2, or 3, or 6. But if they ever ask you to find the cube roots of unity, it means find the cube roots of 1. So if you set up an equation like this, okay, I did a specific one with a 4th power, but this exponent can be anything. In the last problem, it was a 3. If you solve an equation that looks like this, essentially what you're doing is you're solving for the nth roots of the number 1. Because you would add the 1 to the other side and take the nth root on both sides.
What's the nth?
We're actually gonna do that one right now, x to the 4th minus 1. And it's a lot easier than doing x cubed minus 1. You'll see why. You're not, well, it's a lot easier. What's the last thing? Okay, so let's see if we can solve that one that I circled. 0 equals x to the 4th minus 1. That's the next problem. Find the 4th roots of unity. 0 equals x to the 4th minus 1. Now, what did we do first on the last problem to turn the cubic into a quadratic? And what did we even have to do before the synthetic? We had to find a root to use with synthetic. And that's normally what you would have to do here. Do the P's and Q's. And 1 does work, so you could divide through synthetically by 1, and then this exponent would drop to a 3. And then it turns out if you divide by -1, that also works. Then you would have to do synthetic division again and turn it into a quadratic. But you don't have to use synthetic division here, or the rational root theorem, because that is factorable. How would x to the 4th minus 1 factor? Yeah?
It's different to squares, so it'd be x squared plus 1x squared minus 1.
Right.
In fact, the x squared minus 1.
And you can factor it again as x minus 1, x plus 1. The only point to the rational root theorem in synthetic division is to get your problem factorable. If you can get it factorable and avoid that, like we did here, great, that's easier. Now set all your factors equal to 0 and solve. How many answers are we expecting from a 4th root problem?
At least 4.
Exactly 4.
Oh.
Exactly 4. So let's do these first. What could you plug in there to get 0?
1.
Okay, so I'll write the answers. X equals 1. How about over here? -1. And now let's look at this one. X squared plus 1 equals 0. So x equals a positive or negative square root of -1. Well, what's the positive square root of -1? I. What's the negative square root? Those are the 4th roots of 1. 1, -1, I, -I. If you want to use synthetic division because you find it fun, exciting, and exhilarating, then go ahead. You could. You'd still be doing the problem. It's going to take you a while, but it would work. Good practice. So as we've been going through it, I've been saying this all along, that the total number of answers that you get is always equal to the degree of a polynomial. That's important to know. I'm not worried about this. But that's not just true in examples 4 through 6. That's true in examples 1 through every example. Okay? So all examples, the number of answers is equal to the degree of the polynomial. That's how many roots you get. But we know that the number of roots you get has to be the same as the number of what else that you get? What's another? Well, roots and zeros are synonyms, so the number of roots is the same as the number of zeros, which is the same as the number of factors. So, if we have to factor a polynomial of degree n, it will factor into n factors. So a cubic would factor into 3. And at this point, I would expect you could do that because all the factors here are nice numbers. If you use the rational root theorem to make your p's and q's, plus or minus 1, 2, 3, 6, and then q is just plus or minus 1. Look at your roots. They come from the p's. So you would be able to get these numbers on your own. If they didn't come out nice, then you wouldn't. Okay, but you should be able to factor something like that now on your own. Find one rational root, divide through by it synthetically, take your quotient, which will now be a quadratic, and factor. Doesn't matter if there's more than one rational root, which this one has 3, doesn't matter which one you divide through synthetically by. Pick any one you want. If you divide through by, well, that won't work because x minus 6 is not a factor in this case. Yeah, you'd get a remainder of non-zero. So yeah, you couldn't use this. The 6 doesn't work, but -1, -2, and +3 will work, and those are all your p-values. The other thing is, roots don't need to be distinct. Okay, this would come from a 5th degree polynomial. What 5th degree polynomial, I don't know. I have to FOIL that out and see. But this comes from a 5th degree. But it has what we call repeated roots. It has -1, -1, 2, 2, and 2. That is 5 answers. They're not 5 unique or distinct answers. There are repeats. But there still are 5 answers. That's important to understand. They are not always distinct. So in this case, -1 is a root of multiplicity 2. And that just means it repeats 2 times. And 2 is a root of multiplicity 3. Multiplicity is how many times it repeats itself. Questions on that? All right, so we'll look at some problems in the homework that ask you to find, for example, a polynomial with certain roots. If I said to you, find a polynomial that has roots of 2 and 3, what would you write down as the factors? X minus whatever the root was, and x minus whatever the root was. Now think of this exactly the same way. Your roots are 2 plus 3i and 2 minus 3i. What would your factors be? X minus 2 plus 3i and x minus 2 minus 3i. So what you end up here is when you find a polynomial that has roots, these i's should all disappear. So you have x minus 2 minus 3i, that's the first one, and x minus 2 plus 3i. let's FOIL that and see what happens. What's x times x?
X squared.
X times negative 2,
Negative 2x.
and then x times 3i.
3xi. 3ix.
Yeah, that's going to go away, so it doesn't even matter. What's negative 2 times x?
Negative 2x.
Negative 2 times negative 2. And negative 2 times 3i?
Negative 6i.
Negative 6i. And the last one, negative 3i times x?
Negative 3ix.
Negative 3ix. Negative 3i times negative 2?
6i.
Plus 6i. And negative 3i times positive 3i. Yep, which is
Just 9.
positive 9.
Oh, yeah.
What cancels out there?
The ix's.
Positive 3ix, negative 3ix,
The i's.
the negative 6i, the positive 6i. So basically, any multiplication that had an I in it, you could have just skipped. So if you have to do anything with an I, you can skip it. And you get x squared minus 2x minus 2x is minus 4x plus 4 plus 9. So there's a quadratic that has 2 plus 3i and 2 minus 3i as its roots. If you use the quadratic formula on that, you will get the roots we started with. Okay, so sometimes that trips up people because there is one like that on the test, finding roots. But just remember, skip all the multiplications with I because they're going to disappear anyway. Right? The only one that's important was this last one because that technically it has an I, but it's an I squared. That's not an I. I squared turns into negative 1. That's different. But we can practice another one of those tomorrow if you want. Okay, so the homework, it's on 193, and we will take a look at that tomorrow and finish up everything for the week tomorrow. Bless you.